disappointed.
Thank you. All right, so radioactive decay and half-life. So you guys should remember that I told you that when something is radioactive, the nucleus is changing, which means it's changing from one element to the next. So since it's changing, you're losing the amount of that element that you have. You say it's decaying. So over time, there's less and less of that element that you had. So if you have, thorium, and over time it turns into whatever it turns into, either actinium or radium, then over time you'll have less thorium. It's going away. So that's why we say decay. All right, so you might think that decay would happen in a way where the same amount goes away every day. Like each day you lose 5 pounds of the stuff until there's none left. And that would be called linear, right? Linear. So linear looks like this. We'll make a little table. Amount and time. And it doesn't matter what our units for time are. We'll say they're years. It could be days, it could be seconds, whatever. Hello?
Where can I find Stacy?
She will have class in that room next period.
Thanks.
So let's say we start out with 1,000 grams of some substance at time 0. Science, we like to say the beginning is time 0. And so let's say every day, or every year in this case, we lose 250 grams. So after 1 year, there's 750 grams left. And then after 2 years, there's 500 grams left. And after 3 years, there's 250 grams left. And after 4 years, there's 0 grams left. That would be a linear decay. If you were to graph it, it would make a straight line. That's why we call it linear. It's the same amount every time. But it turns out that radioactive decay doesn't happen that way. Radioactive decay is actually exponential. In fact, a lot of types of decay are exponential. The way your body removes substances from it is exponential. The amount that decreases is a lot at the beginning and then less over time, and it takes a long time to get rid of all of it. So I'll show you what exponential looks like. Exponential. All right, so we'll do amount and time. Let's start with our same 1,000 grams of the substance.
Is it a year frame?
Yeah, we'll do years again. So we'll start with our 1,000 grams at time 0. It's supposed to be a 0. And what will happen is after a certain period of time, and we're going to go with 1 year again, half of the substance is going to be gone. So after 1 year, we have half of it left, 500 grams. But now, after another year, we're going to have half of what's left. So at year 2, we have 250 grams left. And at year 3, we have, oops, it's supposed to be 3. We have how much? 125 grams left. And at year 4, we have 62.5. And those are at 62.5, right? There we go. So every year it gets cut in half. And if you do the math, technically the line never hits 0, right? But eventually there's such a small amount it doesn't matter anymore. So that's what exponential decay looks like, and this is what actually happens. The amount of the radioactive substance goes away a half every so often, whatever its half-life is. Okay? Now, to use this, to be able to calculate how much is going to be left after a while, we need an equation. And we will call this the half-life equation. In fact, you've probably seen this equation in math class many times. It's also the same type of equation you would use to calculate interest over time and things like that. So it looks like this. P, which stands for the present amount, which is really the end amount, So let's say it's the end of some time period, equals the amount that you started with times 0.5, because it cuts in half every time, to the power of, and I'm going to move some space so you can see this, it's going to be time that passed divided by,
That's a T.
that's a t, divided by the half-life, which will be t with a little half under it. Okay? So it's time divided by whatever the half-life. Now in this problem, I made the half-life 1 year, right? But for other substances, it may take 5,000 years for half it to go away, or it may take 1,000,000 years for half it to go away. But you'll know what the half-life is. You'll look it up on a table. It'll be some number that you find on a table. All right, so there's our equation. P equals A times 0.5 to the power of T over T with a little subscript 1/2. All right, let's do a problem. So let's say, I don't have any problems written down, I should have. So let's example one. If we start with 12,000 grams of, let's say, carbon 14. How much will be left after let's say 40,000 years? Okay, so my T is 40,000 years. And my amount that I start with, so my A is 12,000 grams. And then T half you would look up on a table. And I have here for carbon 14, T half is 5,730 years. So that's how long it takes. That's the half-life of carbon 14. So it's how long it takes for half of it to decay. So right now you would know that after the first 5,730 years, I would have 6,000 left, and so on and so forth. But after 40,000 years, we will have how much? So we're going to do P equals, and just plug in numbers. 12,000 times 0.5 to the power of 40,000 divided by 5730.
I'm sorry, where did you get the 5,730?
That came off the table. And on your worksheet, I will give you a table with a list of the half-life for a few different things. So you you would just look up carbon 14. If you didn't have the table, you could Google carbon 14 and you would find it. Okay, so when you do this math now, what are you going to do? Well, first we need to do 0.5 to the power of this. Then we'll multiply by 12,000 afterwards. Now, find the fraction first. Do 40,000 divided by 5,730. And then, hit enter, and then do 0.5 to the power of that. Otherwise, your calculator is probably going to screw up. So this should be about 7 or 8 or something.
It's 6.9.
What is it?
6.9.
So you're going to do 0.5 to the power of 6.9 what?
I don't know. It was,
6.9. And then you're going to multiply by 12,000. So you're doing it last like that. You're doing this part first, then this part, then times 12,000 will be the last step.
Or 41,000. Is that right?
No. You multiplied this first and then raised it to that power, I think. So do 0.5 to the power of 6.9.
Oh, to the power.
To the power.
I don't think I could do that.
You can. I'll show you how to in a minute. 100 what?
100.47.
200?
100.47.
100.47. Exactly 100?
Little arrow thing?
Grams.
You know what they're saying?
You should have a caret button on your calculator that looks like this,
Turn it sideways.
and that button is the to the power of
I don't
sign.
have that.
Or you'll have a y to the x on your thing. Right there, see where it says y to the x? So you're going to hit 0.5, hit that button, and then hit 6.9. Yeah, either you're going to have a caret button like this, or you're going to have something on your calculator that says y to the power of x. Either one does the same
Let me
thing.
get that.
Let me see.
That's what I got.
divided by x. 6.9. Okay. No, that's not right. Let's do the calculator work. This 6.9. That's what you do. So you got to type in the exponent first. Y to the x, yeah, so you're going to hit 6.9, y to the x 0.5, yeah. Usually they do it the other way. Okay, and then times 12,000.
So wait, to get to that answer, you just do 25
0.5
times,
to the power of
and then you
6.9.
multiply it by,
After you get your answer, multiply with 12,000. All right, you guys want me to do another problem?
no.
Okay, let's do one more.
Mrs. Strip Matter, please call 2501. To reset Strip Matter, please call 2501. Thank you.
Let's do, if we have 3,000 grams of uranium 238, how much will be left after, I don't know, how much time you want?
10 minutes. 12 minutes.
Okay, we gotta convert it to years though.
12 years.
12 years. All right, 12 years. Question mark, right? Be more proper. All right, so A is 3,000 grams. T is 12 years. And here's the fun part. Uranium-238 has a half-life of 4.46 billion years. Somebody who's good at math, tell me approximately what the answer is going to be.
But,
All right, don't plug it in. If you think about it, you can kind of guess about what we're going to get for our answer, though. Because if half this stuff decays in 4 billion years, how much is going to decay in 12 years? Almost nothing, right? Our answer is going to be pretty close to 3,000. We'll plug it in, though. Let's see what happens. So here's what we have. P equals 3,000 times 0.5 to the power of, and it's going to be 12 divided by 4 billion 460 million. There we go. So your exponent's going to be almost 0. So plug it in. Tell me what you get.
2.69.
For what? This? But that's got to be times 10 to the minus, like, the same. What's it say?
10 to the minus 9.
Okay. All right. So do 0.5 to the power of that. 0.5 to the power of your answer. Don't type it in. Hit second answer. What do you get? All right. I'm going to plug it in. So here's what happened. We picked such a small time. Our exponent is going to be nearly 0. 12 divided by 4, 4, 6, 0, 0, 0, 0, 0, 0, 0. So it's 3,000 times 0.5 to the power of 0.0000000026.
Oh, man,
5 to the power of 0.00000026. So what you get is 3,000 times 0.0999999999, and somewhere at the end there's an 8 too. So what's that going to come out to? It's about 3,000. 0.99999 is basically 1. So
Yeah,
almost
that's a bad
nothing
number.
decays in 12 years. If I give you a bigger number, we would get something else. You good? All right. That was a lot of fun, right? Questions?
No.
Okay. I guess that confused everybody. I should have picked a bigger number. Last year Sarah's fault. She picked a number.
You asked us.
I did. sound mad about it. I was like, turn the camera off, please.